All right, here we are. It's the last section of the class, polar functions. We'll start off with a quick review of pre-calc once again. There are four equations that you need to know. And if you know these four that I put in this lovely multicolored box, you can do any polar problem ever made. Three of these four come directly from SOHCAHTOA, and the other is the Pythagorean theorem. They're all based on the above drawing. Your positive x-axis is sometimes called the polar axis, and the origin, once in a while, people will refer to it as the pole. Actually, hardly anybody says that. Usually we call it the origin. And then you have the radius, r, that comes off of the origin. And normally we're used to x comma y, which are called rectangular, or sometimes called Cartesian coordinates, after famous mathematician and philosopher René Descartes. In the polar world, it's radius comma angle, r comma theta. All right, if you look at it, this makes sense because x squared plus y squared equals r squared is simply the Pythagorean theorem. The others come from SOHCAHTOA. Tangent is opposite over adjacent, which is y over x. Also, when you think about it, the slope of the tan line is the derivative, and slope is y over x, rise over run. Sine is the y, so tangent is sine over cosine. That kind of makes sense as well. And then if you want to get either one of these two on the left, just think of theta. Let's do sine of theta. Sine of theta, as we know from SOHCAHTOA, is opposite over hypotenuse, which would be y over r. And if you cross multiply, you get y equals r sine theta, which is one of the two. You can repeat the process to get the other equation with the cosine. So again, if you can't remember those, you can always make the drawing and reinvent them, but they're super useful and you probably want to commit them to memory. All right, we're going to try a couple pre-calc examples before we get into the calculus. We want to convert from polar to rectangular coordinates and then sketch the graph. All right, well, first things first. Right now it is in polar. I see this 4 cos theta. I don't know what to do with it, but if I multiply it by r, and I multiply the other side by r, I have 4 r cos theta. And hopefully r cos theta rings a bell because r cos theta is x. So the right-hand side of the equation is 4x. The left-handed side, here is r squared, and of course r squared is just going to be x squared plus y squared. All right, so hopefully by now you can tell that this is going to be a circle. Let's get a 0 on the right. So we'll go ahead and go x squared minus 4x. Leave a little gap. Plus y squared equals 0. And we'll do everybody's favorite algebra activity, completing the square. Divide the negative 4 by 2. That's going to be minus 2. Square that. So we're adding 4. So you have to add 4 to the right-hand side as well. That becomes a trinomial. You can see that these two match each other. Just for fun, the y squared, I'll call it y minus 0 squared, just so we can see the center. And 0 plus 4 is 4. This is a circle. It's centered at 2, 0 with a radius of 2. Remember, that's r squared. So you go 2 left, right, up, and down. A lot of students say the trickiest part of this is actually making a round circle. Not to brag, but that's not too bad. All right, so I did it. Let's see. Convert from polar to rectangular. That's right here. And sketch the graph. That's right there. Okay, good pre-calc. Let's do another. Same sort of thing. I'm not a big fan of cosecant, so I'm going to rewrite this problem before I get started. We have r equals negative 6, and of course cosecant is simply 1 over sine. They're reciprocals. So I'll write it like that. And I'm going to just cross multiply. Let's give that a 1. And we'll cross multiply right now. So we're going to have r times sine of theta, which makes r sine theta. Hopefully that sounds familiar. Equals negative 6. And if r sine theta sounds familiar, it's because it's y. So the rectangular equation is y equals -6. And obviously when you graph that, it's just going to be a horizontal line. Right here at -6. There you go. We converted from polar to rectangular and we graphed it. Okay, let's go right to calculus now. Okay, here's where it's going to get real. We want to find dy dx and the slope of all the tan lines. Well, first of all, a couple of the tan lines are completely obvious. The slope right here is 0. The slope right here is 0. The slope here is unknown, but it's going to be negative. Okay, so we'll come back to that. And we have to find dy dx, which will help us get the third and final slope. As we know, dy dx is dy d theta over dx d theta. So let's find those first. Before we find dy d theta, we need y. And y, of course, is r sine theta. But r is that. So really, we're going to have sine of theta times quantity 2 plus 3 sine theta. I'm going to further rewrite this using distributive property. That's going to be 2 sine theta plus 3 sine squared theta. All right, so that's y. Now, if we take dy d theta, we take the derivative of it. The derivative of 2 sine of theta, of course, is 2 cos theta. Plus, over here we're going to use the power rule. 2 times 3 is 6. Sine of theta to the first, so I don't need my parentheses, times a chain rule of cosine theta. All right, so that's going to be dy d theta. I'm going to sort of hide that up in the corner so I still have it. And I'm going to erase my work so I can figure out what dx d theta is. Okay, we know likewise that x is r cos theta, but we know r already. Same thing, it's still 2 plus 3 sine theta. So x is going to be cosine theta times 2 plus 3 sine theta. Okay, again, I'm going to go ahead and just try to work this out. I'll distribute it. X is going to be 2 cos theta plus 3 sine theta cos theta. And finally, we're going to take the derivative of that with respect to theta, dx d theta. The derivative of 2 cos theta is going to be negative 2 sine theta. Really, if I wanted to get clever, I could turn this into a double angle, which would be 2 sine theta cos theta, just, kind of use a 2/3. But I think I'm just going to suck it up and use a product rule. I'll call the u the 3 sine theta and the v cos theta. And so when I do u prime v plus uv prime, I'm going to get plus 3 cos, so that's plus 3 cos squared theta, minus 3 sine, so minus 3 sine squared theta. Okay, that's dx d theta. Okay, so dy dx, the problem says find dy dx. So I'm going to take my dy d theta, which I hid up here. I'm going to bring it back down. I've got my dx d theta on the bottom. I'm going to stack them into a fraction, and that will be that answer. Okay, so there's the dy dx. Now to find the slope down here, which is the last thing that I need, I look here and I see the point r theta. This is in polar coordinates. Theta is pi. So all I have to do is replace all these thetas with pi's, and I can figure out what the slope is there. All right, let's give it a whirl. Of course, sine of pi is 0. So this is 6 times 0 times negative 1. That's gone. Sine of pi, again, is 0, so these are zeros. Cosine of pi is negative 1, but you're squaring it, so that's going to be 3 times 1 down there. That's 3. Again, cosine of pi is -1, so 2 times -1 is -2. And the slope at the other location is -2/3, which looks about right from the drawing, down 2/3. All right, there we go. We've got the dy dx, which unfortunately I've sort of defaced, and the slope of all three tan lines. The first two were easy, they were 0. The last one I had to work for. And that's it for number 3. You can see this is getting a little tougher. This is a tough section. Number 4 wants us to find the derivative dy dx at theta is pi/2. All right, well, once again, dy dx is going to be dy d theta over dx d theta. And we don't have x and y quite yet, so we have to go get them. Again, from our lovely formula rainbow box, y is r sine theta. And over here, x is going to be r cos theta. If you don't have those memorized, eventually you will, whether you mean to or not. Okay, so y equals, and of course r we know. So I'm going to try to kind of jimmy this a little bit. I'm going to take this, put it here. I'm going to say 3 sine theta, and then the parentheses next. And then I'll go and distribute it. Okay. Over to the x. Again, x is r, but we know what r is. Cos theta. So again, I'm going to go 3. I'll use this cos theta first. And I'll plug the r in, which is, I've already used the 3, so just another 1 minus cos theta. Whew. Okay. So now I have to figure out what dy dx is. And as I mentioned earlier, dy dx is just dy d theta over dx d theta. So I'm going to take the derivatives of each one of these. All right, I'll start with the y. The derivative of 3 sine theta will be 3 cos theta. Unfortunately, here I have a product rule. That's going to end up being 3 cos squared theta. And of course, it's minus because there was a negative there already. Negative times negative, because the derivative of cosine is negative sine. Double negative, so this will be plus 3 sine squared theta. That was a bit fast. You may want to go back through there yourself and verify what I have, just to make sure you agree with me. All right, and then the dx d theta, the derivative over here, derivative of 3 cos theta will be negative 3 sine theta. And here, again, this is like having 3, instead of having the square there, let me just bring it out here, that'll be easier to see. That's going to be minus 6 cosine of theta to the first. But the derivative of cosine, the chain rule, is negative sine theta. Negative sine theta. But the negative will turn this other negative into a plus. So you'll end up with a plus 6 cos theta sine theta. So there's dy dx. Now we're just going to go ahead and plug the pi/2 in for all these thetas down here. So we'll have 3 cosine of pi/2. Well, cosine of pi/2, cosine of 90 is 0. So that's gone. All the cosine of thetas are going to be zeros, including this, which is going to knock all this out. That's a lot easier. And then the sine of pi/2 is 1. So right here we have 3 times 1, which of course is 3. Down here, this sine of theta is going to, or I should say sine of pi/2 is going to be 1. So that's negative 3 times 1. That's negative 3. And that makes the overall dy dx, the slope, negative 1. And theta is pi/2. Okay, hopefully that made sense. You will be asked to find the location of horizontal tangents and vertical tangents. At first, when I read this, I thought it was backwards again because horizontal tangents are where dy d theta equals 0. But I thought, well, that makes sense because if y is not increasing or decreasing, if you're coming along like this and suddenly you flatten out and then you go backwards, right here is a horizontal tangent because y isn't changing. dy d theta is 0. And same thing for the vertical tangents. If you're coming along like this and you turn that way, that would be a vertical tangent because x isn't moving. You're not changing left or right. And obviously if they're both 0, just like in the other section, you can't make any conclusion. If dy dt and dx dt were both 0 when we were doing parametrics, you couldn't draw a conclusion about tan lines. All right, we're going to go ahead and find the points of horizontal tangency and vertical tangency to the following polar curve. We'll start off with the horizontal tangents. In order to have something be a horizontal tangent, dy d theta has to be 0. Let's go ahead and find y. Y, of course, is r sine theta. But we know what r is, so r times sine of theta. So y is going to be sine of theta minus sine squared of theta, or sine of theta getting squared. And then we can find dy d theta. The derivative of y with respect to theta is going to be cosine of theta minus 2 sine of theta to the first times a chain rule cos theta. Okay, again, we want to set that equal to 0. And when we do that, we can go ahead and factor. We can factor out a cosine of theta. That leaves me with 1 minus 2 sine theta equals 0. That tells me that either one of two things is true. Either the cosine of theta is 0, or 1 minus 2 sine theta is 0, meaning that sine of theta would be positive 1/2. Okay, so I just said that either cosine of theta is 0, or sine of theta is 1/2. Well, where does that occur at? The cosine of theta is 0 at pi over 2 and 3 pi over 2. The sine of theta is equal to 1/2 at pi over 6, which is 30 degrees, and 5 pi over 6, which is 150, quadrant 2. All right, so those so far are the places that might have horizontal tangents. I have to kind of keep those in mind because remember, dy d theta is 0, but you also have to make sure that dx d theta is not 0. So we're going to put those on hold before I make the claim. In fact, not all 4 of those are going to be legit answers. One of them is going to get banished. Now we move on to the vertical tangent locations. Again, to be a vertical tangent, we need dx d theta to be 0. Well, again, let's figure out what x is. X is going to be r cos theta. Of course, here's r. R times cos theta. Again, a little distributive property. It's going to give us cos theta minus sine theta cos theta. Unfortunately, we're going to need a product rule on the second part when we take the derivative, but that's okay. We can get that. So here we go. dx d theta, the derivative of x with respect to theta, is going to be negative sine of theta. Again, we've got the correct letter. We've got a product rule. Okay, like I mentioned. So I'm going to make this negative sine theta. We'll turn that into the u. And the cosine of theta will be the v. And so I'm going to go u prime v, which will be negative cos theta times another cos theta, that's minus cos squared theta, u prime v, plus u, which is just negative sine theta getting copied, v prime. But the derivative of cos theta is negative sine theta. So another negative sine theta. Negative times negative is going to be positive, and you'll be able to square the sine theta. So dx d theta is equal to negative sine theta plus sine squared theta, but minus cos squared theta. Woo! All right, that's not going to be as easy to factor. I'm going to have to pull some trickery here, and I'm going to change the cosine squared of theta using the golden sheet to 1 minus sine squared of theta. That's going to get distributed through. So you're going to have negative sine theta minus 1 plus sine squared theta plus this other sine squared theta. So I'm just going to slip a 2 in and make it 2 sine squared theta. And again, just like before, we want that to be equal to 0. So I make that equal to 0. I'm running out of room and I still have to factor, so let me come up here and rewrite it. And as I rewrite it, I'm going to write it in purple in descending order. So I'll have 2 sine squared of theta. I hope you're good at factoring. Minus sine of theta. Minus 1 sine of theta. Minus 1 equals 0. Some people like to replace the sine of theta with a variable because they don't like the trig in there. I think I'm just going to tough it out. This is going to factor into 2 sine of theta and just sine of theta, because that'll make the 2 sine squared. I know the only way to get the minus 1 at the end, 1 is just 1 times 1. I just have to put the negative on the right spot here, and it's going to be in the second parentheses, because that way you're going to have negative 2 sine theta, positive 1 sine theta. That makes negative 1 sine theta in the middle, so that's correct. So that means that sine of theta is either negative 1/2, that'd make the first parenthesis 0, or sine of theta is going to be positive 1. So where does that occur? Before I get too far, let me throw the negative sign in that I missed. Okay, where is sine of theta negative 1/2? Where does that occur at? Well, it occurs in quadrants 3 and 4. One place would be 7 pi over 6. And the other would be 11 pi over 6. That's the quadrant 4 location. Where is sine of theta 1? Well, sine is the y. The only place that's going to happen is pi over 2. Okay, so you've got to have points of horizontal and vertical tangency. And we have all these different theta values. But remember, we got to go back to the other slide to make sure that none of them repeated. We've got pi over 2, 7 pi over 6, and 11 pi over 6. And the pi over 2 repeats. Okay, so pi over 2 is banished. These are okay. Let's go back to the other one. Pi over 2 repeats. These are okay. But the bad news is I just found theta angles, and the directions say find the points. So I have to put them back in and figure out what x and y are. All right, no problem. We're going to do this. Okay, I went ahead and graphed the shape, which actually looks like a large green unripened tomato or maybe a green heart. There's an official name for it later on in one of the subsequent slides. But you can see the 3 horizontal tangent points, 0, negative 2, plus or minus rad 3 over 4, comma 1/4. And then there's a pair of vertical tangent, points of vertical tangency at plus or minus 3 rad 3 over 4, comma negative 3/4. I did that by taking the green angles that you see and then slowly, painstakingly plugging them in to make sure that I got the answers. So, wow. These problems are taking a while, as you can see. Again, don't be intimidated by them. I know that it's a little harder doing it this way, but we'll get there.